Hello, my name is Jared Hudnall, and today I'm here to present my final exam submission for Physics 177, Computational Methods for the Physical Sciences at UCR. So let's get into it. So first I will navigate to uh, my final exam file. So there's a couple of files associated with my program, and I'm going to demonstrate it in the kind of this Ubuntu terminal that I have set up rather than Google Colab because some of the functionality of my program is not compatible with Google Colab. I will explain exactly what that is and why Google Colab doesn't work when we kind of get to it, but in the meantime, I'm just going to kind of introduce it here. So there are three files associated with my program. Um, but before we kind of hop into it, I'll do a quick demonstration and load up into an IPython environment. And we'll run the randomwalk.py file, which essentially acts as like main.py for my project directory. Um, so we've run it, nothing's exactly happened, except we have some added functionality. And in particular, there's a class that's been defined that we have access to now. So I'll kind of demonstrate a couple of instances of that class. So we'll create an object of the class associated with my program. Um, and we'll start first with, in particular, my program is actually defines a random walk and plots the random walker and has some functionality associated with animating the random walker. So the class is walker. Uh, we'll do 3D. And the object of this class is, we'll name him Fred. And Fred is going to go on a random walk. We're going to go make him do 100 steps, for instance. And now that Fred's gone on his walk, we'll plot his history. And now we have Fred, and it's pulled up an instance of a matplotlib um, figure, and we see Fred going on his random walk with a step counter up on the top left. And it stops at 100 because we had Fred go on 100 steps. So that's pretty cool. There's a little bit more. Um, we can also create maybe another instance of a slightly different class, which is Walker 2D. And this time we'll call him Tim, and we'll give Tim a couple of arguments, actually. Um, one is we'll set Tim's name. Maybe we'll call him Timothy. And we'll pass Tim a color, say red. Okay, so similarly, Tim will go on his own random walk. Maybe he goes for 120 steps, for instance, and we'll plot his history after he's gone on his walk. And instead of a 3D random walk, we now have a two-dimensional random walk with a more kind of canonical matplotlib pyplot. And this time, of course, okay, so we can kind of see the uh, the consequences of these arguments. So the plot's name is replaced with the name that we pass into our object, and of course the lines associated with Tim's random walk are red. These black lines here are associated with boundaries. So I could have done this program without imposing any boundaries on the random walk, but I thought adding boundaries into it was kind of a fun challenge and made it kind of more interesting. So these black lines represent boundaries that Tim is not allowed to cross. Actually, you couldn't see it because it wasn't uh, visualized, but Fred had similar boundaries. He was confined to a three-dimensional cube and was unable to leave that cube. So actually, what we'll do maybe is let's open up a new terminal, and just for fun, we will open up another IPython environment. We will run randomwalk.py. We will create a new one. Let's call her Samantha. She will be Walker 3D, and I don't know, color will be black. And Samantha is going to go on a walk for, let's say, a very long time. Float object cannot be interpreted as an integer. Oh, that's disappointing. Okay, so we'll just add a bunch of zeros then. Uh, we'll let that go for a while. And we'll be well, I guess I'll kind of minimize this and let that run, and we'll return to it in a few minutes and maybe get a chance to plot some of this history, because that'll be fun, I think. So okay, now that we've kind of seen the demonstration of the program, let's walk through a couple of the files. So first, the randomwalk.py file that we actually ran in the IPython environment is a very simple program. It only has 2 lines. The first line is to import this walker class from randomwalk3D and import the walker class from randomwalk2D, and it names them 2D and 3D respectively. So okay, fine. Then all of the actual code must be contained within randomwalk 2D and 3D. So we'll run through those files really quick. So first we'll go through randomwalk 3D, and there are uh, 3 packages that we need to import for this. So the first is we'll import NumPy, because we always import NumPy. We need matplotlib.pyplot, which is, I don't think is surprising. And then there's this third one as well, which is matplotlib.animation. And from this is a module from matplotlib that kind of, as the name implies, animates things, and we can import this function called funcAnimation from that module. And we'll talk more about kind of what that is and what that's doing and how that works kind of towards the end of the program. And then the only other thing before we kind of jump into this walker class is we've defined this global variable called boundaries, and it's just a list that contains 2 integer elements, -3 and 3. And very quickly, I think we'll get into exactly what that is. But as you can see, this is the whole program. So it's all contained within this walker class, all of the functionality. So let's jump into it. So classes in Python are essentially ways that the user can define their own data types. So if you're not happy with the kind of default data types that Python has, you can create a class and then define some functionality associated with a brand new data type, in this case, a random walker. So the first thing is we have this def init, which is the initialization for the walker class, and it has a couple of variables associated with it. The first is self. This is Python's way of kind of organizing and differentiating one instance of a class from another. So this is always passed as an argument to all of the initialization and to all of the subsequent methods associated with this class, which is uninteresting. So there's nothing being changed. This is just the object is being passed around all of these methods when these different methods are called for a particular object. So the first thing we have is we have the associated with each random walker is a position, a history, a name, and a color. And each of these are initialized first to none, which is a kind of keyword in Python, which tells Python not to really associate this variable with anything. So we're declaring it, we're saying that it exists, it's going to be there, but we're not assigning it to anything yet. It's kind of a null like type. But importantly, when the user calls an instance of a class, the user has the option to initialize these variables with other things, and that's kind of where this none functionality is going to come in. So, in particular, if we look at the position attribute first, so if position is none, that is, if the user hasn't changed it, the class is defaulting it to none, and if the user hasn't changed it, then it's still none. Then we initialize the position to this numpy array of 0, 0, 0, which is the origin of our coordinate system, casted as floats, which is what these decimal points are doing here. And then otherwise, that is, if the user has changed has called an instance of a class and passed along a position variable, then we'll go ahead and take what the user passed in and then cast it as a numpy array. Same for history. So if history is none, then it will be, by default, it will be an empty list. And otherwise, it'll be whatever the list is that the user passed along. The name is by default Walker, otherwise it's the string that the user passes, and the color is by default blue unless the user passed in a different color, in which case it's that one. And that's also passed along as a string. So that's all of the attributes associated with this class, and now we jump into some of the functionality, which is associated with methods in that class. So the first method we'll talk about is the inbounds method. So inbounds returns a Boolean, which is to say it returns true or false if certain conditions are met. And it takes in one argument, which is the a position vector. So this is not necessarily the position that the random walker is at, but this is just any vector in three-dimensional space. In particular, it's looking for a list. It doesn't actually have to be a NumPy array. It could be just a regular array, but um, that is it requires this argument for the inbounds Boolean expression. And we'll see kind of what this method is doing in our program a little bit later. But first, we'll see how it works. So there are three variables that we're interested in. There is in x bounds, in y bounds, and in z bounds. And these are also all three Boolean expressions. So if we look at in x bounds, what this is it checks if the position vector that we passed into this method, if the first element, which is to say the element that is associated with the x-axis, is greater than boundaries 0, the first element of the boundaries list, and less than the second element of the boundaries list. So now we see kind of what the point is of this boundaries variable. So this boundaries variable is what we're checking the position vectors against to see if it's if it's within certain bounds, right? So what this is saying is, okay, is the x position of this vector greater than the lower bound and less than the upper bound? And if it is, then in x bounds will return true. Similarly, for in y bounds and in z bounds, it will just check the second and the third indices of the position vector, which are associated with the y and the z axes. So then we have the if expression, which actually determines is the inbounds method going to return true or false, and it only returns true if the in x bounds and in y bounds and in z bounds, all three are returning true. Then we return yes, the random walk or the position vector that you passed in is in the bounds of that we've specified. In particular, the bounds here being -3 and 3. So okay, that's the inbounds method. It's not clear where that's going to come into play just yet, but we'll actually see immediately in the next method, which is walk. So walk is where all of the kind of interesting physicsy stuff is. So walk is how our random walker is actually going to go on his random walk, and it takes in one argument, which is the number of steps that you want the random walker to take. So for example, actually let's check up on Samantha. Samantha's still going on her walk. She might not finish in the next half hour. I might have added a few too many zeros, but we'll see. but this is this is how you call the method, right? So Samantha is an instance of the walker class, and we're calling the walk method by doing Samantha.walk, and then we're passing in the number of steps. In this case, it looks like how many millions? 100 million steps? Yeah, that may take a little longer than I'm anticipating. In any case, so when the walker method is defined, you enter into this for loop, which indexes over this kind of dummy variable I with over a range of the number of steps that you passed in. And then it enters into this loop that many times. And the very first thing we have is while true, which implies that there's going to be some kind of break condition. So it's going to try something again and again and again until some condition is met, in which case it'll break out of it. But before we get into the details of the walk, let's look at a quick picture that I prepared, which is position vector 3D. So here we have I wish that, okay, perfect. So this is, of course, a unit position vector in spherical coordinates for three dimensions. You have an x and a y and a z. So any arbitrary position vector in three-dimensional space can be defined in terms of the Cartesian unit vectors x hat, y hat, and z hat, like so. So you have the polar angle, theta, and the azimuthal angle, phi. Theta goes from 0 to pi, and phi goes from 0 to 2 pi and wraps around. And you have kind of this projection of the Cartesian unit vectors based on the values of theta and phi. I don't think this is uh, particularly advanced material, but we're going to use it here. So we have two variables that we have the opportunity to randomize. So this is how how the random walker is going to go on his random walk. We're going to have this kind of unit position vector. So every one of these vectors associated with any values, any arbitrary values of theta and phi will have a length of 1. And if we randomize the values of theta and phi, we essentially get a random position vector in three-dimensional space, which is how we're going to execute our random walk. So let's see that in practice. We have theta, which is again the polar angle that goes down from the z-axis, is assigned a random variable between 0 and pi with numpy's random uniform uh, module. And then similarly, phi is randomized in the same way, except that the range is allowed from 0 to 2 pi, as mentioned. And then now that we have these two random variables, that's all we need to really put together our random uh, position vector. So we have this new variable that we're going to call step. It's going to be a numpy array, which is going to make it compatible with the numpy array position vector that we have assigned to the which is associated with the attribute that we've defined for our walker class. And here we have exactly the same thing as in the picture. We have uh, sine theta, cosine phi for the first index associated with the x direction, sine theta, sine phi associated with the y direction, and cosine theta associated with the z direction. Now we have this if statement. So this is where now we see the functionality of in-bounds, the in-bounds method. If self.inbounds, if this walker is inbounds and we pass along, again, a position vector, we need the position vector to check if that position is in bounds. If the walker's position plus this step, so we have this kind of vector addition of whatever the walker's current position vector is, we do a vector addition of this randomized step of length 1, and we pass that into bounds, and then we check, is that position vector in the bounds that we set for our random walker? And if it is, then we will enter into the if statement, and we'll we'll update the walker's position by adding the step. So in here, this is just what we're passing into the inbounds function. It's not actually updating the position of the random walker. So this actually commits the step to the walker's position, and it appends the history attribute that we also defined for our random walker, so that we can plot the history and we can keep track of where the random walker has been and where it's going over time. So we append to this random walker's history attribute, we append a copy of its position vector. And then we break because we had a while true loop that we entered. And so we can see now, okay, there's no else for this if, because uh, if it's the case that the position vector that we're looking at is not in the bounds, then it won't break out of the while true loop, and it'll just go back and it'll create a new set of randomized theta and phi variables. It'll create a new step variable, and it'll recall inbounds, and it'll keep on doing that again and again and again until inbounds returns true, and it commits this position. And then once it's done that and it's broke out, it enters back to the for loop and updates the index I. So it will keep on, this index only updates when this kind of step function has successfully updated the walker's position, and it has actually taken the number of steps that we told it to take. So the next method is plot history, which is the final method of the program. It's also by far the most complicated, but we'll run through it. So we have no attributes or no arguments other than self for this method. It just takes the history attribute of whatever the random walker is that you've plotted the history of. So we'll do this slowly. So we have first plot style used, Seaborn, V0 dark plot. This is just something that makes it kind of look pretty. Oh, killed. Oh no, Samantha, RIP. Okay, let's create. I really want to get like a really nice long walk out of this. So let's create a new Samantha. We'll call her Samantha 2. Samantha 1 is no longer with us. So she'll be a three-dimensional walker, and I think I want color black. So we'll do that. And Samantha will go on random walk. We'll go 100,000 steps. Okay, that was much better. And now we'll plot Samantha's history, and we'll let that run for a little while in the background, I think. Cool. So back to the plot history method, and we'll return to see Samantha's, the kind of end result of Samantha's walk when we're done. We have this kind of just visual element, and then we have, so moving on to the actual guts of the plot history method, we have two objects, which are fig and x, which is a figure object associated with matplotlib and an axes object. So fig is always just plot figure. We don't need any arguments, nothing fancy. Fig.add subplot goes into x, and this 111 is associated with one column, that would be one row, one column, and it is the first of the axes objects. And we're telling matplotlib that this x object is not going to be just confined to x and y directions. It's going to be a 3D component as well. It's going to be a z component. So we set the limits on our x, y, and z boundaries. So this is just what is matplotlib going to actually show. So in particular, it's going to be one lower than the lower bound and one greater than the upper bound. Just so we have a little bit of give, and we know that the random walker isn't going to get past that. We set x, y, and z labels, pretty straightforward. And then we set the title, and the title is whatever the name attribute is of our random walker with a font size of 16. And then we have labels. So the labels for the random walker are actually not set. You can see that they're not there. Just as kind of a visual choice, but x labels is a new variable. This isn't something that matplotlib isn't looking for something called x labels. This is a new list that we're creating, and it's going to be this empty string. So it's a list of empty strings for this dummy variable underscore in the length so x labels is going to be of the length of the number of ticks on the ax object. So ax has a method called getXTicks, which just returns an integer number of x tick marks that matplotlib has decided to assign to the ax object. We convert that to, or we get the length of, okay, sorry. Ax.getXTicks returns a list of all of the x ticks that matplotlib has defined. So it's a list that it returns, or an array. And len gets the length of that list of x ticks, and then range converts that number to basically be compatible with this for loop that we're indexing over. So x labels is literally just going to be a list of empty strings of a length that is the same length as however many x ticks there are on the x object. And the y labels and the z labels are the same. And then we do have this ax.setXticks, which just puts all of the x ticks of the ax object to what they ought to be, and sets the labels to this empty list. So this effectively, all of this together effectively removes the labels from matplotlib. So it doesn't plot, it'll show the ticks, you'll see the tick marks, but it won't have any numbers associated with the x and the y axes, which is just a kind of a visual thing that I wanted that's more kind of general. Okay, So moving on to uh, the next part kind of gets into the animation of the program. So this is the thing that Google Colab is unable to do, as far as I know. Google Colab is not compatible with the Func animation function from Matplotlib animation, and so that's the reason we're kind of going through it on this kind of separate terminal-based environment. So, but I'll still put all the code into a Google Colab link and share that as well. So we create an object called line, which is going to be um, just as a bit of context. So what we're doing here is we're going to define two variables that we're going to, the way that Func animation works is that it defines a number of frames, and then every frame passes along this update function, and uh, this update function will run after every single frame. So it updates the frame. It tells Matplotlib what do I change every frame uh, as I go along. What am I animating exactly? And so we're going to have it animate two things. So there's going to be two variables that it's going to update every frame. The first is the line. So this is literally the line that kind of connects the position of the random walker to the next position of the random walker through the series of steps. Um, so that is going to be uh, uh, an ax.plot object with pass along as we're going to initialize the line as being um, empty x, empty y, empty z, and the line style is solid with some marker and marker size, and then the color associated with the color attribute that we defined for the function. And we're going to update this line variable again and again and again later. But first, we're kind of declaring these variables, and then we'll initialize them and update them in the next two functions that we'll define in this method. The second thing that we're going to update every single frame is step counter. So step counter is going to be a two-dimensional text, which is this, right? Samantha's going on quite a walk. And you can see the boundaries are certainly working. She's pretty well confined to this box. And you can see her step counter is updating here. So this is what is meant by a 2D text. Yeah, 2D, yeah, text 2D is a method from the ax associated with the ax object that creates literally a two-dimensional ax object, and we associate it with some position 0.02, 0.95, and this transform thing tells it kind of where to that it can use the go outside of the axes. Um, it can live, and that's where the step counter will be. It will be we're at first making it just an empty string, but of course we'll change that in a font size of 10. So okay, now we can get into this init function, which is an initialization not associated with our random walker class, but rather an initialization of these two variables that we're going to update in the frame. So line is going to, it has um, two methods associated with that we're going to take advantage of that comes with matplotlib and the ax object and how ax.plot functions. First is set data. So this is going to be an initialization of the data that's associated with the line object. And it's going to be at first two empty lists associated with the x and the y coordinates. And then because we have a third dimension, we have but matplotlib kind of by default uses two dimensions. We have this separate method to initialize the z direction to an empty list. And then we'll also initialize the step counter. So the step counter at first will literally just say step. And then it'll have its colon and it won't tell you what step. I guess there could be step 0, for instance. And then it'll return a tuple of the line and the step counter. And then similarly, we have update, and update takes in an argument of the frame. And the frame, this is a number, it's just an int that tells you what frame you're on. So we pass along what frame we're on, or what's the kind of the last current frame, or the last frame. And now we're updating to a new frame, which will be frame plus 1. So we have this x, y, and z variables, which are going to be associated with just a list of all of the x positions of the random walker for it's actually going to be a list of lists, right? So the first element of the list is going to be the first set of position vectors associated with, or this first position vector associated with the random walker. And then say if you're on frame 5, right, you're going to have element 1 will be where it started, and then element 2 will be where it was in the second frame, in the third frame, in the fourth frame, in the fifth frame. So X, Y, and Z are very complicated, like lists upon lists, and it'll update every time. So this update is what we're going to pass along into the line object. So we're basically grabbing, okay, at frame 20, where was the random walker? And not only that, but where was the random walker at all in all the frames previous? And that's what the X and Y and Z variables, that's the information that the X, Y, and Z variables store. And then we pass those X, Y, and Z variables into the line object. So that is how we're updating the line object. And then we update the step counter. And we set the step counter to have a text that displays step, and then frame plus 1, whatever the current frame now is, which is associated with frame plus 1. And we return again a tuple with the line and the step counter. And now we have everything we need. We can use finally call our func animation function that we imported at the start, and we'll call it anim. And func animation takes in the figure object that we created, the update function that we just defined. It takes in however many frames that you want, which is just the length of the history attribute. So however many steps that the random walker is taken, it'll take up that number of frames. And then we have an initialization function that we also defined called init. And then there are a couple of other optional arguments here. Blit equals true. I believe just makes it so that matplotlib won't update the entire plot every single time, every single frame. It'll only update things that have actually explicitly changed. So it just makes the animation run a little faster and a little easier to process because it's not doing everything from scratch again and again. We have this interval, which is 200, which is the time interval between frames, which is defined in milliseconds, so 200 milliseconds between each frame. And repeat equals false just says we don't want the animation to repeat when it ends. It'll just end. We see we're not going to have that problem with Samantha because she's not going to finish her walk before we close her. And then the very final line of the program is plot.show. And that, of course, just we did all this work plotting this, and now we'll pull it up. So that is the entirety of the random walker 3D function. It's been I think I'm a little bit over time already, but I wanted to talk about the 2D. There's some other things that you can do with this that are very interesting that would be that I've played around with a little bit, but didn't have time to talk about in this video. So some other things that you can do with this that are pretty interesting is if you remove the boundaries, for instance, you can show with NumPy you get like NumPy mean, and it would be something like NumPy mean of like self.history if this was inside the class. And what this would do, for instance, is grab the average value of the history. You might need to actually, because this history is contained of vectors, this might be more complicated than that. But things like that, and things like getting the standard deviation of the random walker's walk are pretty interesting because we've done some derivations in advanced statistical mechanics this quarter with deriving the variance of a random walker. And I've tested it before, and of course this function actually, if you remove the boundaries and do some work, and you can get a kind of like experimental quote unquote values for the standard deviation of a random walk, which is supposed to be the square root of n, which n is the number of steps, and it's this program very closely mimics that and shows that that's true, and you get very close. If you have 100 steps, you get very close to a standard deviation of 10. But of course, if you put on boundaries, then the standard deviation is going to be a lot artificially lower, especially for Samantha, for example, right? Because her standard deviation, you can see, is not going to be square root n. It's going to be way lower than that. But okay, so did I make a? I don't think I made any changes. So we'll quickly run through random walk 2D because it's very easy. It's almost the exact same, but there are just a couple of differences. So in particular, the differences are instead of a three-dimensional NumPy array, we use Python's complex class or data type, which is inherent in Python. Which I mean, you could have just made this a two-dimensional Python array, but this was more interesting to me and just a better opportunity for me to learn a little bit more about Python. And I really like that you can deal with complex numbers. So the self.position variable in this case, instead of being initialized to a three-dimensional NumPy array with 0, 0, 0, this is a complex number that starts with a 0 on the real part and a 0 on the imaginary part. And everything else is the same. Instead of in x bounds and y bounds and z bounds, we have just x bounds and y bounds, and global boundaries is not. That was I made a mistake. Now, instead of calling before, this was position 0, the index, the first index of the position list or NumPy array. This time we have position.real. This is the real part of this position object, which is pretty interesting because it's a complex number. You have a real and imaginary part. So the real part is associated with the x-axis and the imaginary part is associated with the y-axis. And we're just checking if, again, is the real part kind of greater than the lower bound and less than the upper bound and yada yada. But some slight differences. The way that we're performing the random walk is only marginally different. So if we go here, we can do position vector 2D. So we have this new position vector, which is just a two-dimensional unit position vector, which only has one random variable associated. It's just polar coordinates, right? It's got one random variable associated with it, which is the polar angle theta, and you have cosine theta times x hat, sine theta, y hat. And so we grab some random uniform variable between 0 and 2 pi, and then a step is a complex number with cosine of theta and sine of theta, exactly as we said. And then it does the exact same thing. It tests if the walker's position plus the step is in the given bounds or not, yada yada. Everything's kind of the same. This is the only kind of addition is I actually plotted the lines for this random walk, for the 2D random walk. So for example, if we, I don't know, what's another name for, we'll call it Perry, is 2D walker. Perry goes on a walk for 50 steps, Perry.plot history. Okay, you see the black lines that we have for the two-dimensional random walk are right here. This is where they're plotted. Then we have x limits, y limits, labels, the update frame. Again, the only difference being instead of indexing over a NumPy array, we're grabbing the real and the imaginary parts of the position object. But that's everything. Yeah, as you can see, they're pretty close to one another, the 3D and the 2D random walk, but it was fun. There's some marginal differences. Thank you for your attention, and thank you for listening, and the opportunity to kind of learn a ton of Python and a ton of how to do physics through Python. And awesome. I'll leave it there. Goodbye.